Hi friends, this is not a music class. I'm going to use this vinyl record player to explain the concepts of uniform circular motion in a simple and practical way. First, a big thanks to the YouTube team for sending us this gift. See, it has our Manocha Academy logo on it. Now I'm going to place this coin on this record player and let's turn on the record player. So when I move the needle here, as you can see, the disc starts rotating. Can you see what is the motion of the coin here? It is in circular motion. And since its speed is constant, this is called uniform circular motion. So remember, a body is said to be in uniform circular motion if it moves in a circular path at a constant speed. What are some other examples of uniform circular motion? It can be the tip of the second hand of a clock, the rotating fan blades, a merry-go-round, or a satellite orbiting the Earth. In all these examples, the object is rotating in a circle and it is moving at a constant speed. So these are all examples of uniform circular motion. To understand and describe uniform circular motion, let's discuss some basic concepts like angular displacement, angular velocity, time period, and frequency. So let's dive into these concepts. Now let's look at our record player. As you can see, the coin is going around in a circle. Let's draw a line from the center of the circle to the coin. This line is the radius of the circle. If we give it a direction, we can call this the radius vector. As the body moves in a circle, the radius vector will move along with it. We can define the angular displacement of the body as the angle swept by the radius vector in a certain time interval. For example, if the body moves from here to here, then it has covered an angle of 60 degrees. If it moves a little further ahead, the angular displacement is now 90 degrees. Now if it moves here, as you can see, the angular displacement is 180 degrees. And when it completes the full circle, what will be the angular displacement of this coin? That's right, 360 degrees. You can measure angular displacement in degrees, but the SI unit is radians. And you know the relation between degrees and radians? That's right, 360 degrees is 2 pi radians. So for a 90 degrees angular displacement, the displacement in radians is going to be pi by 2 radians. For a 180 degrees displacement, it's going to be pi radians. And for 360 degrees, the full circle, the angular displacement will be 2 pi radians. Angular displacement is a vector quantity, but what is its direction? Note that it is not along the angle. Angular displacement is an axial vector. Its direction is along the axis passing through the center of the circle. But is the direction outwards or inwards? You can easily find this by using the right hand thumb rule. Just curl the fingers of your right hand in the direction of the motion and the thumb will give you the direction of the angular displacement. And that reminds me, don't forget to hit the like button for this video and share it with your friends. Alright, let's continue on the right hand thumb rule and use it to find the direction of the angular displacement of this coin. So as you can see, the coin is moving around like this, and if I use my right hand, I need to curl my fingers in this direction of the right hand, right? And where is my thumb pointing? As you can see, the thumb is pointing downwards. So basically, the direction of angular displacement is going to be inwards over here into the circle, this way. How is angular displacement connected to linear displacement? Linear displacement means the displacement along a line. So here, as the coin moves, it is the displacement along the tangent to the circle. Now from mathematics, we know that angle equals arc divided by radius. If the angle is denoted as theta, arc as s, and radius as r, we get the formula theta equals s divided by r. So angular displacement is linear displacement divided by the radius. And if you rearrange this formula, you will get s equal to r theta. This expression tells us that if the angle is the same, as the radius increases, the displacement will increase. You can practically see this if I place another coin at a different distance from the center of the circle. As the record player rotates, what is the angular displacement of both these coins? That is the red and yellow coin? That's right, it's exactly the same because both coins are covering the same angle in the same time. So they are having the same angular displacement. But what about the displacement or the distance covered along the circle? Clearly you can see that the yellow coin is covering a smaller distance since it is closer to the center. And the red coin, which is further away from the center, is covering a much larger distance because the radius is more. For the yellow coin, the radius is smaller. For the red coin, the radius is larger. So therefore, the red coin is having a larger linear displacement. And this is exactly what we expected because the formula is S equal to R theta. So greater the radius, more will be the displacement. So you can see the red coin is covering a much larger distance as compared to the yellow coin. The yellow coin rotates in a small circle, but the red coin is rotating in a much larger circle, even though both are having the same angular displacement. So remember the relation S equal to R theta. Here theta is the angular displacement. Its unit is in radians and it is an axial vector passing through the axis, which is the center of the circle here. And S is the linear displacement or the tangential displacement along the tangent to the circle. And they are related with S equal to R theta, where R is the radius of the circle. So remember this important formula. S equal to R theta. It is connecting the angular displacement with the linear displacement. We know that a body in uniform circular motion has an angular displacement. And since the body is in motion, it will have some velocity. That is angular velocity. Now how do we define angular velocity? Remember, velocity is the rate of change of displacement. So similarly, angular velocity becomes the rate of change of angular displacement. Velocity, the formula is displacement divided by time. So similarly, angular velocity, the formula is going to be angular displacement divided by time. And we denote that as delta theta by delta t. Delta theta is the angular displacement and delta t is the time. And angular velocity is denoted by the symbol omega. We use this Greek symbol and the lowercase symbol omega here. So omega equal to delta theta by delta t. That's your angular velocity formula. Now can you tell me what is the unit of angular velocity? Angular velocity is angular displacement divided by time. So the unit is going to be radians divided by seconds. That is radian per second. Now let's say our coin here covers 360 degrees, that is 2 pi radians in 2 seconds. So what will be its angular velocity? You can use the formula omega equal to delta theta by delta t. Now substitute the delta theta, which is the angular displacement, as 2 pi radians, and the time to complete this motion, to complete the circle, is 2 seconds. So it's going to be 2 pi divided by 2, which is pi radian per second. That is the angular velocity of this coin. Or if you want the numerical value, that's going to be 3.14 radians per second. Now note that this is the average angular velocity, omega equal to delta theta divided by delta t. But if the time interval delta t is very, very small, that is in the limit delta t tending to 0, our formula becomes omega equal to d theta by dt using calculus. And this is the instantaneous angular velocity. That means the angular velocity at any particular instant. So that is omega equal to d theta by dt. We have to do the differentiation with time here. So remember, the average angular velocity formula is delta theta by delta t, and the instantaneous one is d theta by dt. Time period is defined as the time taken by the body to complete one revolution along the circular path. This coin here is taking 2 seconds to complete one full revolution. So what is the time period? The time period is going to be 2 seconds. Time period is denoted by capital T and its unit is seconds. Now what is frequency? Frequency is the number of revolutions completed by the body in 1 second, or we say in unit time. Frequency is denoted by F, or you can use the Greek letter nu. I like to use F for frequency. It's simpler. Now what do you think is going to be the frequency of this coin? Since it takes 2 seconds to complete one revolution, so in 1 second it's going to complete half a revolution. So the frequency is half. The SI unit of frequency is 1 by second, or denoted as hertz. So frequency of this coin is half hertz or 0.5 hertz. So remember, time period is the time taken to complete one revolution and frequency is the number of revolutions in 1 second. So time period and frequency are the reverse of each other. And the relation between time period and frequency is T equal to 1 by F or F equal to 1 by T. So as you can see, they are reciprocals of each other. How are angular velocity, time period and frequency related? It's very simple to derive the relation. Start with the formula of angular velocity. We know that angular velocity is angular displacement divided by time. Now if you take the time as the time to complete one full revolution, then the time will be the time period capital T, because it is the time taken to complete one full revolution. And what will be the angular displacement in one full revolution? That's right, it's going to be 2 pi radians because you're completing the entire circle. So what is the angular velocity? The angular velocity is going to be 2 pi divided by T. So that's our important relation. Omega equals 2 pi by T. And remember, 1 by T is the frequency. So we can also write angular velocity omega is 2 pi F. 2 pi times the frequency. So see, it's so simple to derive the relation. When a body is in uniform circular motion, we talked about two displacements. Linear displacement or tangential displacement, that is measured along the tangent to the circle, and angular displacement, that is the angle covered. Similarly, we can have two types of velocities. We can have linear or tangential velocity and angular velocity. Let's look at what is the relation between linear velocity and angular velocity. Linear velocity, or simply velocity, is the rate of change of displacement. Linear velocity, the formula is v equal to ds by dt. Remember, linear velocity is along the tangent to the circle at a point. So we can also call it the tangential velocity. And angular velocity, our formula was omega equal to d theta by dt. Now how are these two velocities related? To derive the relation, let's start with the formula angle equal to arc by radius. So remember, we talked about it, that theta is s divided by r, or delta theta is delta s by r. Now if we divide both the sides of this equation by the time delta t, we are going to get delta theta by delta t equal to 1 by r times delta s by delta t. Now in the limit delta t tending to 0, we get d theta by dt equal to 1 by r times ds by dt. So angular velocity omega is going to be 1 by r times the linear velocity v. Or you can write it as v equal to r omega. So linear velocity equals radius times angular velocity. So larger the circle, that is for a larger radius, linear velocity will be larger. As you can see, with these two bodies placed at different distances from the center of the circle, both the bodies are covering the same angle in the same time. So their angular velocity is the same. Now, is the linear velocity of the two bodies same? No. As you can see, the yellow coin appears to be moving much slower compared to the red coin. The red coin is moving much faster. with a greater linear velocity. Why? Because it is covering a larger circle. So larger the radius, obviously the linear velocity is going to be larger. Since angular velocity, linear velocity and radius are all vectors, we can use the vector notation in the formula and write it like this. We had similar relations for displacement and velocity. Remember, we saw S equal to r theta, and here we have V equal to r omega. So in both these equations, we are multiplying with the radius of the circle r. So it's easy to remember, S equal to r theta and V, the linear velocity, equals r times omega, the angular velocity. Is uniform circular motion an accelerated motion? What do you think? We are tempted to say no, since the body is moving at a constant speed. So acceleration should be zero, right? Remember, acceleration is defined as the rate of change of velocity. Velocity is a vector quantity. It has both magnitude and direction. In uniform circular motion, even though the speed of the body remains constant, the direction of the body is constantly changing. At a particular instant, the direction of the velocity is a tangent to the circle. And as the body moves in circular motion, the magnitude of the velocity remains constant, but the direction of the velocity keeps on changing. So the velocity is constantly changing. Now, since the velocity is changing, the body must be in acceleration. So uniform circular motion is an example of accelerated motion. Now, what is the value and direction of the acceleration here? Since the tangential velocity is constant in uniform circular motion, the acceleration cannot be in that direction. That is, it can't be in the tangential direction. The acceleration has to be perpendicular to the tangent. That means perpendicular to the tangent to the circle at any point in the body's motion. If the acceleration is perpendicular to the tangent, that means it is along the radius of the circle. Acceleration is always along the radius towards the center of the circle. Since the acceleration is always center seeking, it is called centripetal acceleration, because the word centripetal means center seeking. Now, by using some vector addition and similar triangles in geometry, you can work out the formula for the centripetal acceleration here. You can refer to your textbooks for the detailed derivation. And finally, you will arrive at this formula, AC equal to V squared divided by R. I'm using AC over here to denote that it is centripetal acceleration. Now, if you substitute V equal to R omega in the equation, AC equal to V square by R, then you'll get another formula, AC equal to omega square R. So both formulas are correct. In one, we are expressing centripetal acceleration in terms of the tangential velocity V, and in the other one, we are expressing it in terms of the angular velocity omega. So remember these two formulas. Centripetal acceleration is denoted by AC. In some books, you'll find it denoted by AR. Here, R stands for the radius, because it is the radial component of the acceleration. It's along the radius and center seeking. So remember to write down and remember these formulas of centripetal acceleration. So uniform circular motion is definitely an accelerated motion. Till now we have discussed uniform circular motion where the body is moving in a circle at a constant speed. But what if the body is moving in a circle at a variable speed? Take the example of a rotating fan. If you consider the blade of the fan, it is initially at rest. And when you switch on the fan, it starts rotating and slowly gains speed, right? So it is definitely accelerating. Is the angular velocity of the fan increasing in this case? The answer is yes, because when you switch it on, it goes faster and faster. So the angular velocity is definitely increasing. This means that there must be some angular acceleration. Now, if you consider the tip of the fan that has just been switched on, the tip of the fan is also moving faster and faster. So there is linear or tangential acceleration as well. So let's look at angular and linear acceleration for circular motion and what is the relation between the two. We know that acceleration is the rate of change of velocity. Similarly, angular acceleration is the rate of change of angular velocity. Angular acceleration is represented by the symbol alpha. So we can write the formula: angular acceleration alpha is delta omega by delta t, where delta omega is the change in angular velocity and delta t is the time. So alpha is delta omega by delta t. This is the formula for average angular acceleration. Now, as the time interval delta t becomes really small, that is the limit delta t tending to 0, we get instantaneous acceleration. That is alpha equal to d omega by dt. Now, what is the unit of angular acceleration? It's going to be radians per second square. Now let's take a look how angular acceleration is related to the linear acceleration, or you can call tangential acceleration. For that, we will start with the equation linear velocity equals radius times angular velocity, or v equal to r omega. Now differentiating both the sides of the equation with respect to time, we get dv by dt equal to ddt of r omega. Since the motion is in a circle, the radius r is constant. So we can bring it out of the differentiation here. So we get dv by dt equal to r times d omega by dt. Now dv by dt is the rate of change of linear velocity. So that is linear acceleration. And d omega by dt is the rate of change of angular velocity. So that's going to be angular acceleration. So as a result, we get a equal to r times alpha. So linear acceleration is r times the angular acceleration. And in vector notation, you can write it as a equal to r times alpha with the arrows on top of the quantities, since they are representing vectors. So remember the important relation that we saw. Linear acceleration is radius times the angular acceleration. So in a circular motion, there can be three types of acceleration: angular acceleration, centripetal acceleration, and linear or tangential acceleration. Angular acceleration is the rate of change of angular velocity. And remember, it's an axial vector. It is along the axis of the circle and it is in the same direction as the angular velocity. The formula for angular acceleration is alpha equal to d omega by dt. Its unit is radian per second square. Centripetal acceleration, on the other hand, is directed towards the center of the circle, and its formula is AC equal to v square by r, or AC equal to omega square r. Linear or tangential acceleration is the acceleration along the tangent to the circle. To make it clear, we can denote it as AT so that you don't confuse it with the other accelerations. And the formula of AT was r times alpha, the angular acceleration. So AT equals r alpha. When the body is moving in a circle and accelerating, it will have two accelerations in the plane of the circle. One is towards the center of the circle, which is centripetal acceleration, and the other is tangential to the circle, that is tangential or linear acceleration. Now these two accelerations are perpendicular to each other. Both these accelerations, centripetal acceleration and tangential acceleration, have the units of meter per second square. So we can find the net acceleration by adding these two vectors. And the magnitude of this net acceleration will be A net equal to square root of AT square plus AC square. We are basically using the vector addition and Pythagoras theorem here because both the accelerations are perpendicular to each other. So this was for circular motion. And note that when a body is in uniform circular motion, that is when the body is moving at a constant speed, angular acceleration and tangential acceleration are both zero. In uniform circular motion, the only acceleration is centripetal acceleration, the acceleration towards the center of the circle, since the direction of the velocity is constantly changing, but the magnitude of the velocity is constant. So you only have centripetal acceleration in uniform circular motion. I hope the concepts of uniform circular motion are crystal clear to you now. Now let me ask you a question. Let's say we have a body of mass 5 kg, which is revolving in a circle of diameter 14 centimeters at 300 rpm, that is 300 revolutions per minute. Now I want you to calculate the linear velocity and centripetal acceleration experienced by this body. Do let me know your answers by putting it in the comments below. I promise to reply to your answers. So do try this question and put in the answers in the comments below. So the next time you're sitting on a merry-go-round or you're watching the second hand of the clock ticking, remember the concept of uniform circular motion. And if you like this video, hit the like button right now and share it out with your friends. And if you haven't subscribed to our YouTube channel, what are you waiting for? Click the subscribe button right now and click on the notification bell so that you don't miss out on any of our videos. And do check out the full courses on our website manochaacademy.com and our Android app Manocha Academy. You can try our courses for free by clicking the Start Free Trial button. To make it easy, I'll put the links below. We have courses on physics, chemistry, biology, maths, coding, and artificial intelligence. In our courses, you're going to get live classes, interactive videos, quizzes, questions, mock tests, and revision notes. So what are you waiting for? Do check the links below and share it out with your friends. So stay connected with Manocha Academy and just keep learning.